A regular tetrahedron has four faces, each of which is an equilateral triangle. A wooden puzzle consists of several pieces that can be assembled to make a regular tetrahedron. The manufacturer wants to package the assembled tetrahedron in a clear cylindrical container with one face flat against the bottom. If the length of one edge of the tetrahedron is 2a, show that the volume of the smallest possible cylindrical container is 8 times root 6 over 9 pi a cubed. Now this is a regular tetrahedron, so the four faces are equilateral triangles. So all edges of this tetrahedron have the same length. In this case the length is 2a. The fact that it's a regular tetrahedron means that this point here is directly above the midpoint of the circular base of this cylinder. This point here is actually the circumcenter of this triangle, the triangle that's lying on the base of the cylinder. The circumcenter is the center of a circle that can be drawn through the three corners of the triangle at the base. Here I have the base triangle drawn out here to show you how to get the circumcenter of it. What we do is we get a perpendicular bisector of two sides. So we could bisect this side, get the midpoint of it, and then draw a line that's perpendicular to this side, so that this distance here is half the total this side. So this distance has to be a. And similarly over here, this is a. Then we get a second perpendicular bisector. So we could bisect this side here, just get the midpoint of this side, and draw in a line that's perpendicular to this side. So this is another perpendicular bisector. Then where the two perpendicular bisectors meet, we have the circumcenter of this triangle. So if we put the center of our circle here, we can draw a circle that passes through the three corners of the triangle. So we need to just get the perpendicular bisectors of any two sides of the triangle. I chose this side and this side here, but I could have got the perpendicular bisector of this side, and if I did that I would find that the three of them perpendicular bisectors are concurrent. The three of them meet at this point. Now because this triangle is an equilateral triangle, if we extend this down here, we'll find that this angle is 30 degrees. The three angles in an equilateral triangle are 60 degrees each. So by symmetry, the perpendicular bisector of this side here of the equilateral triangle will actually bisect the angle here. So here we have an angle of 60 degrees. We divide by 2 to get 30. We can now look at this right angle triangle here. We have an angle in it other than the 90 degree angle, it's 30 degrees, and we have a side which is 1a. So this green triangle here corresponds to this one in here. What we can do is get the other two sides of this right angle triangle. That will help us get the height of the tetrahedron. Actually, the best thing to do is to calculate this here, because if we know this, we can get the height. You see that in this right angle triangle here, the side adjacent to 30 degrees is a, the hypotenuse is x, x is what we want. The cos of 30 degrees is adjacent over hypotenuse, or a over x. So we can rearrange this to find out what x is. Basically cross multiply and make x the subject, or simply interchange these two. So x equals a divided by the cos of 30 degrees. The cos of 30 degrees is 0.866, but if you look it up you can get it in surd form. 30 degrees is one of the standard angles. 0.866 is actually root 3 over 2. So we've a divided by root 3 over 2, so I just multiply above and below by 2 here to get 2a over root 3. Now I'm interested in the height of the tetrahedron, which I will call y. So what I will do is I will look at this triangle in here that I'm shading in. This is a triangle that's inside the tetrahedron. It's a right angle triangle. We have a right angle here. That's the angle between the height of the tetrahedron and any line running from the foot of that height along this horizontal plane, the plane of the circular base, or the triangular base of the tetrahedron. So here we have a right angled triangle, so I'll just show it here. So this is y. This here is x, which we just got in terms of a. It's 2a over root 3. And what else have we got? Well, if I draw in this here, that's just the distance up along here. This is just this edge of the tetrahedron. This edge is 2a. So we have two sides in terms of a, and one side missing in this right angled triangle. So we have enough information to find y in terms of a. We can use Pythagoras. So the hypotenuse squared, that's this side squared, is the sum of the squares of the other two sides. Two a times 2a is 4a squared. When I square this thing here, I have 2a times 2a on top, that's 4a squared. Root 3 squared is 3. Then I have y squared. I isolate y squared. So I take 4a squared and subtract this term. I can write 4a squared as 12 over 3a squared, just to get a common denominator. I subtract the 4a squared over 3. So I have 12 minus 4, or 8a squared over 3. And then y is the square root of that. That's the square root of 8 over 3 times the square root of a squared. So I end up with the square root of 8 over 3 times a. This a is not underneath the square root sign. The volume of a cylinder is pi r squared h, where the radius r of this cylinder is the distance from this point to this point here, which is x, which we worked out earlier to be 2a over root 3. The height of the cylinder is this distance y. It's the same as the height of the tetrahedron, because the tetrahedron just fits inside the cylinder. So we have 2a over root 3 squared. That's going to give us 4a squared over 3. 4a squared over 3 is multiplied by root 8 over 3 times a. So we get an a cubed from a squared times a, and the 4 over 3 is multiplied by root 8 over 3. Now the form that we want our answer in is this form here. So we want this number here to equal 8 root 6 over 9. So rather than trying to actually write this thing here in the form that we want, what I will do is I will put this number equal to 8 root 6 over 9 and prove that this thing is true. Probably the easiest way to do this is simply to square both sides. So if I square the left hand side, I get 4 squared is 16 over 9. If I square root 8 over 3, I just get 8 over 3. And if I square the right hand side, I get 8 squared is 64 times 6 over 9 squared is 81. So I'm putting these equal to each other, and hopefully I'll get something that's obvious. 16 times 8 is 128. 9 times 3 is 27. So that's what we have on the left hand side. And if we look at this number on the right hand side, we can divide 6 by 3 to get 2 and 81 by 3 to get 27. So we have 64 times 2, which is 128 over 27. So that shows that we can write the volume as 8 root 6 over 9 pi a cubed. Here is a similar type of problem involving a pyramid. A builder wishes to construct a glass roof for an atrium in the shape of a square-based right pyramid, as in the diagram below. So the base of this pyramid is a square. The length of sides of the base are to be 3 meters with a height of 2 meters. And the frame is to be constructed of aluminium tubing. What we want to do is get the length of tubing. So we want the length of all the edges of this pyramid. Well, we know that the length of the sides of the square base is 3 meters. So we're going to have 4 lengths of tubing, 3 meters each. What we want are the slanted edges. We can look at this right angled triangle here, which lies in the square base. By symmetry, if we get the perpendicular distance of this point here, which is the point directly below the apex of the pyramid, we get the perpendicular distance of it to one of the sides, then it will bisect that side. So it bisects this side of 3 meters into two lengths of 1.5 meters each. So this distance here is 1.5 meters. The base is square, so we know that this angle here is 90 degrees. Okay, all of these angles are 90 degrees inside the square base, the four corners of the square base. So by symmetry, this line here is actually a diagonal of the square base. If I extend this line here out along here, it'll be one of the diagonals of the square base. You can see that for a square, if we draw in a diagonal, we get a right angled triangle here, which has two equal sides. It's an isosceles right angled triangle, so that this angle here equals this angle here. But these two angles have to add up to 90, so they're both 45 degrees each. So that tells us that this angle here must be 45 degrees. That's just by extending this on, and we have a 45 degree angle here, and we have a 90 degree angle down here at the base, at this corner of the square base. That means we can now calculate this distance here. Because we have a right angled triangle, we have an angle other than the right angle, and we have one of the sides, which is 1.5. So I'm going to calculate this distance here, which I'll call x. We need x because we can use x, this x and this length here, to find the length of this edge. So I'm showing this triangle over here. To calculate x, we use the fact that the cos of 45 degrees is the side adjacent to 45, which we have, divided by the hypotenuse, which is what we're looking for. So x equals 1.5 divided by the cos of 45 degrees. We cross multiply, rearrange to get x, or just interchange these two. So x is 1.5 divided by cos of 45, which is 2.12. So this is the two decimal places, 2.12 meters. So knowing what x is and what this distance here is, we can find the length of this edge here. So we just use Pythagoras' theorem to find this distance here, which I'm calling y. To two decimal places, I get y equals 2.91 meters. So that's one of the slanted edges, and the four slanted edges have the same length. They have a length of 2.91 meters each. So to get the length of tubing, we multiply 4 times the length of a slanted edge, which is 2.91, and we multiply 4 by the lengths of the edge of the square base, which is 3, and I have an answer of 23.7 meters.